A graduate of the University of Toronto Faculty of Medicine, Dr. Chin began her medical career practicing family medicine, and in 1994 earned her executive MBA, also at the University of Toronto. Please welcome Dr. Chin.
Thank you, and it's lovely to see electricity in the room. I think everybody knows each other, so we're going to have a lovely evening together. And I'd love to start by saying, I'm home. I used to work at the bank. And there's two people here that I won't point out. One was my boss, and the other one was my first teacher when I was in the operating room, and he or she knows this. I tease he or she all the time. That he knew, or she knew, that we, two ladies, my girlfriend and I, first-year medical students in the operating room, and he or she said, "Welcome, are you two nursing students today?" So, I have redeemed myself today, I hope, by bringing some friends with me. Thank you, Gilles. Thank you very much for hosting, and I want to thank Gilles and his entire Bank of Montreal Private Client Group team, who is led by Betsy Chung and Sarah Scott, and without the two of them, you would not have any water or food on the table tonight. And again, thank you for making possible and supporting the innovation in science. As many of you here might know, the Bank of Montreal has been a major supporter of the Canada Gairdner Awards. How many of you know about them? All right, by the end of tonight, you will know. Given to the world's most creative and accomplished biomedical scientists who have made great breakthroughs, often revolutionary, that lead to diagnosis, treatment, and cure. In the past decade, 19 of 29 Nobel Prize winners in medicine had already won a Canada Gairdner Award. Pretty good track record, eh? I was going to say better than Leafs. Okay, I won't talk about that. Oh, I'm sorry. Okay, that allows you to get here with easy parking, okay? So, that includes Dr. Elizabeth Blackburn, and tonight the Bank of Montreal is supporting Drs. Blackburn and Harley's visit to Toronto. Thank you, thank you, thank you. It makes so much sense that those in business of wealth management want to see their clients not only prosper, but to be well, live long, and enjoy the rewards of their financial success. I think we can all agree on that. To ensure value, they do their research, and we know you expect the same quality from your healthcare provider as well. Which brings me back to Gilles, who recently had his telomeres tested, to experience this breakthrough himself. Now, when it comes to telomeres, length matters. And Gilles, yours are looking great. In fact, so great that I'm going to write you a doctor's note to give to Bill Down that says, Mr. Gilles Ouellet must keep reporting to work. He's going to provide value for a very, very long time. So don't retire. It's because of trailblazers like Dr. Elizabeth Blackburn that I can make that claim. She and her colleagues have given me the science to not only help people see the results of my clinic's health action plans, but to give me the chance to say to every client of mine, I told you so. Eating well, getting enough exercise, and quality sleep do matter. And there is so much more you can do to stay healthier. So 25 years ago, I started my practice. I told people if they just changed a few of their daily habits, they could avoid getting sick. And the response was lukewarm at best. So I stepped it up, and 10 years ago, I launched my integrated personalized health practice that focused on scientific data, information that helps my clients keep track of how well they are performing health-wise. At the same time, Dr. Blackburn and Dr. Harley were both hard at work on their telomere research, And the discovery by Dr. Blackburn with respect to telomerase was recognized in 2009 when she was awarded the Nobel Prize for Medicine along with some of her colleagues. You can certainly read about her amazing research in this week's Maclean's magazines, which you have copies of if you care to pick one up tonight. Because of the gains Dr. Blackburn has made in telomere science today, we have solid proof that better health habits can ward off diseases that can ruin what should be the greatest years of your lives. So enough said on my personal validation. There is so much to admire about Dr. Blackburn. Being involved in groundbreaking research means putting yourself on the line. On one hand, you certainly get acknowledged with a few awards here and there for wonderful things you do, but you can stand for something, but if you do stand up for something that's not the party line, there will be people who try and get in your way. So for example, in 2003, Dr. Blackburn was appointed to President George W. Bush's Council on Bioethics at a time when the politically charged issue of embryonic cell research was making waves, and this president was definitely not in favor of such ideas. Dr. Blackburn supported the research, saying, "You have to do research. You have to get the science right." She also argued that politics shouldn't influence scientific advice. Her term on that council was not renewed. We need more people like Dr. Blackburn. And in the brilliant words of my literary friend Bob Ramsey, who hosted our luncheon today with over 300 people today at the Acadian Room, he said, "The success that Drs. Blackburn and Harley enjoy will definitely have a profound effect on the lives of, well, let me be conservative and say, everyone on Earth." And tonight, we have the pleasure of having both these scientists here to speak to us. So it is my honor to introduce the first of two guest speakers this evening. I present to you Dr. Elizabeth Blackburn.
Elaine, thank you so much, and thank you for organizing this delightful evening and for making sure the weather let me see the lake for the first time I've ever seen it blue. So this is an extra pleasure to have this opportunity to talk to you tonight. Now, Elaine said something that I want to open my talk with, and she talked about how we really want to think about approaching health. The triumphs of medicine have been to diagnose diseases, to treat them, to recognize what's going on in individual severe diseases. But more and more, what we really want to be thinking about is what can we do in terms of trying to not get to the situation depicted here where there's a sort of progression from, being not in a disease state to having an advanced disease state, and then having to call in the firemen, i.e. the medical profession, to rescue heroically, skillfully, bravely what was, a destructive situation, a disease that's already taken hold. So much better as one learns, and that's what's been possible through basic science and clinical advances, so much better to try and think about how would you know what's going on as diseases progress and understand earlier and earlier so that you can preempt them. And that really is not a dream anymore, because through the combined efforts of so much different aspects of science, fundamental science, translational science, clinical science, really a lot has been learned. And so it's not a dream to start thinking, let's try and intercept earlier and earlier. So, preempt diseases before they happen so the house remains intact, because no matter how heroic the fireman, usually there's some damage done or the house doesn't retain its, integrity. So that's the general concept. And so what our research, which Elaine alluded to, took us into was that question through telomeres, the ends of chromosomes. And so these are the protective tips that protect our genetic information, which is on chromosomes. And I'll tell you very briefly about that. But more, I want to tell you about why should you care about that and how that turned out to relate to that question of how do we approach preempting diseases before they take hold. So here is a picture under a microscope of chromosomes, and the blue sausages are the chromosomes that have all our genetic material in them, and the red dots are just a dye that's picking up those protective tips at the ends of chromosomes. And for many years, that's what people knew about telomeres. They were sort of blobs and very important. And so I had the very good luck of being able to analyze what was the actual molecular structure at the ends of these chromosomes. And so to sort of expand it slightly, what I found was that the building blocks of DNA, which of course there are billions of that make up our genetic information all along the end, the length of those blue chromosomes, but the very tips, those protective tips, are made of just very simple repeated DNA sequences that don't code for proteins or genes, but which act as a kind of protective tip. And it's made of simple DNA, and just to put it in a little bit more detailed, if we looked at the very tip, what happens is protected by a sheath of proteins. That's the telomere that we talk about. And it's made of thousands of these building blocks. But the key point is it has to be long enough. As Elaine said, length matters a lot to telomeres, because if that even gets eroded away partly, that doesn't work anymore to protect the ends of chromosomes. That sheath is no longer functional, and that has really severe consequences for cells. So all of this was learned through doing a lot of basic science over the years, and there was a real issue at large here, because we knew that there's a propensity for telomeres to wear down. It's just inherent in how the chromosomes, which have to multiply every time a cell divides, so we have cells dividing all the time throughout our lives in our bodies, we knew that all these special cell enzymes that do this are doing a tremendously good job all the way along the chromosome until they get to the end, and at the end they do a terrible job and they basically can't replicate the end. And so the prediction is, well, we know how these enzymes work, and we know they can't copy all the way to the end. So the chromosomes would just be shrinking away and shrinking away. Clearly that doesn't happen. And the answer turned out to be a gizmo, which I'm just showing as a little picture here. So if we look at the chromosomes and look at the DNA at the very end, this little gizmo I'm showing is the enzyme telomerase that my then PhD student many years ago at Berkeley and we discovered in our lab at the University of California, Berkeley. And this is an enzyme that adds DNA to the ends of chromosomes as the DNA is wearing down. And there's a lot of regulation of this enzyme so that it responds to when telomeres get shorter. So you'd think, well, this is all fine and good, right? Everything's perfect. We know we have a problem, but we've got an enzyme that adds DNA to the ends. So what's the problem? Well, the problem is us. We basically live longer than this enzyme stays active for. And so what happens is that sets up a situation where there can be an imbalance of the adding to the ends, which will maintain the telomeres. So if you have adequate telomerase, and that's the name of this enzyme, that finds the ends of chromosomes and adds and replenishes DNA to the ends. So as the cells keep dividing, what I've depicted is a chromosome end. So if you imagine just one of your chromosome ends, but this is typical, this would be true for all the chromosome ends. Sometimes it gets a bit shorter and sometimes a bit longer because telomerase responds, but overall it keeps its average length, if you have enough telomerase, to be long enough for that protective sheath to work, okay? So the cells can keep dividing. Now, if the balance is off, then we start to see problems which turned out to relate to this question that now all of us are interested in, both individually, from our family point of view, societal points of view, world economic points of view, every point of view I can think of. This question of how we're aging is becoming more and more at the forefront. And of course, it's a multifaceted process, aging, and it has many aspects to it and many facets. But the real one that our work turned out to relate to is the aspect of aging, which is, the least welcome, which is increased susceptibility to those diseases of aging, which account for so much mortality in the developed world: cardiovascular, cancers, diabetes, various, degenerative and other diseases. So those are the ones that go up enormously with age. And that is what this very basic research on the telomeres turned out to be related to. And so in recent years, I've just gotten very fascinated by that aspect. And this probably isn't quite the right quote, but there's a Winston Churchill quote, and it goes something like this. He was talking about military strategy, but he said something like, however beautiful the strategy, occasionally one should look at the results, right? And I sort of think, well, it's a little bit like this in terms of our science, and how does that, beautiful science, lots of groups have done beautiful science, not just us. We were very lucky to be in it very early, but there's lots of beautiful science. But what, the results are, well, what good is that to people, right, in a more practical way? What are the results? And so that's what has been very fascinating, to have great collaborations and really work with people who are interested in what's happening in actual human beings and find out how this science is going on. So the bottom line is that, as I said, there's this enzyme, telomerase, it exists, should be just fine. But the thing is that us as humans, we're just made this way, that we just don't seem to have enough telomerase in the cells. That telomerase is the enzyme that replenishes the ends of the chromosomes. We don't seem to have enough to keep us going, to keep those cells going. So what happens is this kind of shortening does happen. And when the cells, telomeres, do erode away too much, which they can do over time, and do in many cells in the body, it seems, then the ends of the chromosome send off alarm signals, the chromosomes don't work properly, the cells go into what's called senescence, but they also malfunction and become like little rotten apples spitting out bad substances that are pro-tumorigenic, can increase cancer growth, and also pro-inflammatory, can increase inflammation. So bad news. And so the question is, does that process in the cells relate to our trajectory of life? Does our candle burn down, by analogy with what's going on in the cells? And really, is this something that does impact on real trajectories of human life? Or is it just a sort of, irrelevant, right? And always remembering that the enzyme telomerase, which in theory could have saved the cells, it's there. But again, the funny thing is that it seems to be generally not enough to maintain the chromosome ends from this attrition. So it's highly regulated, there's lots of complexity. But the bottom line is that you can sort of think of it this way. If there's enough telomerase, the shortening is going on, but so is the addition. So you end up with a balanced situation. So cells that replenish, for example, our immune systems throughout life, we want them to have telomerase, and they have some, but even so, even those stem cells start to show some attrition, which Peter Lansdorp from Vancouver showed many years ago. So even stem cells that should be replenishing, again, don't quite keep up throughout human life. And then, the good news would be, well, maybe if it's the other way around, maybe cells can actually add more than they lose. This can happen and does happen in the immune system. So that can happen. But very commonly, as I mentioned, the other way happens. So maybe there's some telomerase, but it then it valiantly tries to keep staving off the shortening, but eventually it happens. And if there's even less telomerase, then the senescence comes sooner. Okay, so you get the idea. It's now nuanced. It's, so where is it going to actually be in humans? And there was no way we could know that without actually asking humans. And so this is where the clinical studies come in. And of course, we expect it to be genetically influenced. And I'll say right away that there are rare mutations that clearly show how important this balance is. And I'll show you what when it goes wrong. But most of us, the genetic influences on telomere length maintenance are relatively quantitatively minor in effect. Now, I don't discount them for a moment, because what is going to be very important is how they interact with things that we can clearly quantify, have quantifiable effects. And luckily, those are the ones we can do something about, because unless you chose your parents wisely, you're out of luck with respect to your genes. But the malleable things, it turns out, are things that are in people's lives. And that's what's fascinating, because we find quantitative effects of certain measurable things that are things that we do have some control over. So just let me tell you about the rare genes, the unfortunate rare individuals who have diseases, just because it's not affecting most people, but it was so informative. So in genes that give you only half the amount of the enzyme telomerase, which, remember I said, would then not be able to stave off the shortening so much as if you had the full amount of telomerase. So the roulette wheel of the gene spins, you have the misfortune to have a bad gene that you inherit. The telomeres definitely get way too short compared with most people. And we can measure and we know what most people's telomeres look like. And that has a real impact. And a bunch of things that now start to look familiar, but they're really sped up. Early death, loss of immune function, some cancers go up, certain gastrointestinal lung diseases, even diabetes. But the speed with which these happen is much greater than in people in general. Now, if you look at people in general, so most of us in this room, or if we look at cohorts, and this has been done in literally dozens and dozens, if not perhaps now hundreds of studies, different cohorts, what you find is that short telomeres do look as if they have a real disease impact. And the reason we know this is now that one can measure telomere length. And Cal Harley will tell you in a talk after you've had food, and I'm really sorry, I'm holding you up from food, but Cal will tell you after you're well-fed about that the way that one can actually measure telomeres. We'll just tell you about the fact that you can. So you can measure it. So once you measure it, that's really important. You get real information, and there's a real association with shorter telomeres with diseases. So that association's there, and they are all the important ones of aging, and they overlap with those ones that I said are caused by having not enough telomere maintenance in the rare genetic information, rare genetic cases. And so they're common things, cancers, lung disease, heart disease now, that starts to show up. Now this is much slower, but it's showing up very quantitatively related to the degree of how much shorter than other people's your telomeres are. Cal will show you a couple of examples of that for diseases. But what's happening is that they're predicting, shorter telomeres are predicting onset of these diseases and even onset of death. I'll just show you one example where this is a study, this was not our work, looking at about 1,600 people from the community. They're elderly people, and what they found was they measured telomere length at the beginning of about a 15-year period and then followed people out and said, among other things, who died. I'll just show you this one. And so, regardless of course. And so the longer your telomeres were, the more likely you were not to have died in that period. It just keeps going up and up. Now, in a study that we have done but haven't published, but we've talked about it publicly, is with 100,000 people in the Kaiser Permanente system, the HMO system in Western US. And we've seen the same kind of thing. And even for just within 3 years, if you're in the bottom quarter of telomere length compared with everybody else, and correcting for everything else, you're 25% more likely to die in the next 3 years. It's just a steady increase, just like this. So this is looking very robust, but I also point out it's very statistical. It's not yes, no, it is probabilities. And the interesting thing is that it's independent of a lot of other known mortality factors, mortality risk factors. So it stands out as an independent measure and is underlying for those reasons I told you about, how the cells can't work properly and can't replenish. It's underlying these sorts of diseases of aging, but by no means is the only thing going on. And I want to be very clear that it's only a part of it, but it's sort of this underlying quiet thing that's going on, and then other things happen to make diseases, specifically, certain diseases happen, like diabetes, there would be risks related to food and lack of exercise and so on. Now, the one part that I think really grabbed me and got me fascinated by telomeres in the lives of people was a study where our colleagues at UCSF were very interested in healthy people, but severe chronic psychological stress that goes on for years and years, that's out of their control, very adverse situations. I'll give you examples. And this has long been known to have an impact, for example, on heart disease. There's very clear causality here. My colleague said, I wonder if telomeres are impacted by chronic psychological stress of a severe kind. And innumerable studies now. I won't go through them all, but innumerable studies have just made that very, very clear. And I just found that so fascinating, because this is life, this is real life, right? And this is how the mind is perceiving and dealing with things, and how external events are affecting people's well-being. And there's a whole list of these really very sad-looking, awful things that are happening to people. And we can clearly see, and that's not just us, many, many other studies, we see clear quantitative impacts that persist. Even, for example, in the childhood trauma exposures, these persist into adulthood and middle age even. And even things like low educational attainment, not finishing high school, there's that fact fascinatingly relates to shorter telomeres in even elderly people. And even in the 100,000 people we looked at in our study in California, we saw this. So there's a very clear relationship. We had wondered if it was related to this disease impact, and I really think that that's pretty inescapable, that this is a real contributor. Not the only thing by any means, but it's certainly there. So this one is another kind of risk factor, and this is to sort of, I've depressed you all, so I want to lighten up a bit here. So this is cynical hostility, which is a measure that actually has quite a severe set of risk associations. This is the Whitehall civil servants. So you've all got the picture in your mind now, right, in Britain, right? And so these are elderly to middle-aged people. They've been followed for years, 10,000 of them. This is on several hundred. But interestingly, they're cynical hostility measures, which, by the way, do relate to physical risks of diseases like cardiovascular disease, also related to what their telomere length is. And if you had high cynical hostility, I'm sorry to tell you, your telomeres were noticeably shorter than the other 2/3 of people who were merely medium and low. And I was sort of rather pleased to see that medium is not so bad. In fact, it's not at all bad. You know, as a scientist, you need a certain amount of skepticism. So anyway, this is one of many examples, but it just makes a point that these effects are very clear and measurable, and so less hostile. And now sort of the better news, so is what can you do about this? And so I'm just going to give this example here. Now this is very technical, so listen to my words. This is just to show, yes, we did it all very quantitatively. But this is physical activity measures, what do people do on average? And as you go down, the people in this study did more and more exercise on a daily basis. But it was pretty moderate by and large. Now, what we were looking at was how much is telomere shortness related to severe stress perception in these people by a set of measures. So more exercise, interestingly, all these numbers, just listen to what I say because the numbers are too complicated to walk through. The point was that the more exercise you did, the more the impact of stress got washed away on the telomeres. And so by the time you do, more in a very graded way, eventually we know that people who do too much exercise actually, again with the 100,000 people, their telomeres actually are shorter as though they didn't do any exercise. So there's a real happy medium for exercise, but which is known already. This is right. But this point, but this points to something. But there's a serious point here, which is that it's the shortness that you can attribute to stress, because there's a lot of things playing into telomere shortness, but it's that part that you can attribute to the impact of stress that gets alleviated by the exercise. And I think that's going to be the name of the game. This is a lot of integrated information that plays into this number which you get, which is how your telomere is being maintained. Now, what's also interesting, and I won't take you through all the data, is that you can see people's telomeres getting longer, and certain things can clearly impact on this. And some of them are dietary. One of them is omega-3, which has a very rich, good history for other reasons. But interestingly, that was quantitatively related to increases in telomere length, including in a very recent, smaller study we did, where it was actually a prospective trial. And what was fascinating was that there was a clear relationship with your omega-3 to omega-6 ratio. That was interesting. With your increase in telomere length, even in shorter time as 4 months. But we've seen it in 5-year observational studies. So there are things that are malleable, is the point. And telomeres don't inexorably go down, although on average in the population they do. But we see clear cases where over 5-10 years that can go up in something like a quarter of the population for 5 years, for example. So telomeres are not inexorably shortening. So the interesting thing is that there's a malleable, very statistical, but a malleable marker here. And so I think I'll just finish with this idea that, you know, we sort of go through life on this long road of life, right? And so we can sort of think of the road forking in some way toward, you know, risks of disease being more likely than, say, being on the sort of healthy fork in the road. And we can put telomere loss and telomere upkeep clearly on those two sort of directions, because as you're going through life, what we've found, and I use we now in a very generic way, because I mean a lot of people in many independent studies around the world actually, you know, what you start finding is, okay, genes are going to play a role, and they probably interact with a lot of other things that you can have, you know, this is not inexorable like genes. So adverse childhood events reverberate well into adulthood in telomere shortness, as they do into risks of the sorts of diseases that in turn we know are contributed to by telomere shortness. Chronic stress, I didn't talk about pessimism, but that, fascinatingly, is another parameter where clearly the data came out. So that puts you on that side of the road. And then other things that one can do, and I haven't talked about stress reduction, but there's quite a lot of observational studies and a few very small pilot studies that clearly indicate, again, that maintenance of telomeres is improved, and that sort of pushes you on that side. So the picture we have is like this. You know, we know that these diseases of aging, these ones that account for a lot of disability years, a lot of loss of good quality of life, productivity, all of these sorts of impacts. And I've listed several at the bottom here, like poor immune function, cancers, cardiovascular diabetes, mental cognitive disorders, depressions. A lot of these things are impacted on by a whole combination, all from genetic to non-genetic, and interactions among all of those. And what we now know is, and I put telomeres sort of at the middle of that, not to imply it's the only thing, because we know that there's a lot of other factors that will play in to these diseases, but it looks as though the telomere attrition is a kind of underlying substratum against which other disease-causing processes can have quite severe impacts, and the telomere attrition is giving you a readout of at least one aspect of why all of these diseases so often seem to occur together. These ones of the diseases of aging, even though we often treat them traditionally in very separate kinds of ways. So not only have I come to the end of my talk, I've come to the end of my voice, and so I'm going to say thank you for your attention, and Cal Harley will speak and continue on after we've all had a chance to eat. So thank you for your attention.